What we're going to talk about now is something called conservation of energy. And what we mean by that is that the total energy in any system should be conserved if you're talking about something called conservative forces. Gravity happens to be one of the few forces that in nature it would be considered a conservative force. Friction is not. So friction always dissipates the energy, and your total energy, if you have friction present, will not be conserved. But in the absence of friction, total energy of a conservative force such as gravity will be conserved. So when we talk about conservation of energy, we're talking about total energy conserved. That is to say that the total energy at the start has to equal the total energy at some final state or final position. So let's illustrate this best with a question. When we talk about total energy, energy total is the potential energy plus the kinetic energy. All right, so the total energy, which sometimes the textbook's referring to as mechanical energy because it's the mechanics, motion, kinematics. But the total energy, whether it's mechanical energy you're talking about, is going to be your potential energy plus your kinetic energy. And that's going to stay constant. If this stays constant, if the total energy stays constant, constant, then as the potential energy increases, the kinetic energy will decrease, and vice versa. If the potential energy, did I say that backwards? If the potential energy increases, the kinetic energy is going to decrease to compensate, and if the kinetic energy increases, the potential energy will decrease. So in other words, what I'm saying is if you look at this energy relationship where the total energy is equal to potential plus kinetic, if this total energy here has to remain constant, what we're saying is if you increase this, this has to decrease because it's got to remain constant. So the best way to illustrate this is with an example, and I like the roller coaster example. Let's assume that we have a little roller coaster car, and it's small, so we'll say it's just 100 kilograms, and it's sitting here still at rest at the top of a 40-meter high roller coaster drop. So right here it's going to start, we're going to say it's at rest, so it's not moving. And right here I'm going to ask you to calculate for me the total energy right here at this point. So at this point the total energy is simply going to be the potential energy, right? So the potential energy at this point is simply going to be mgh, which in this case is the 100 kilograms times the 9.8 times 40 meters high, and that potential energy is going to be 39200. So this is 39200 joules of potential energy. What is the kinetic energy here? Well, the kinetic energy is 1/2 mass v squared. But we said right here it's at rest, so our velocity is 0, so our kinetic energy is 0 joules. So the total energy as the sum of the potential energy plus the kinetic energy is going to simply be the 39200 joules plus 0 for kinetic is simply the 39200 joules. That's your total energy at the start of this situation where the cart is at the top, it's at rest. Now the cart is going to go down the slope. As it goes down the slope, see what's happening is it's dropping in height. And remember, potential energy is mg, which that stays constant, but the height's changing. So as the height decreases, the potential energy that this car had at the very top is going to decrease till it hits the bottom. Now right here at the bottom, let's say the car is right here now. At this position here, and let me do this position in blue. What is the potential energy of the car right here? Well, it's mgh, but the height in this case is 0 because it's flat on the ground, and we're going to say ground is reference 0 for calculating potential energy for gravity. So if it's right on the ground, the height is 0, so the potential energy is 0 joules. But what about the kinetic energy? What's the kinetic energy at this point? Well, it's going to be 1/2 the mass times the velocity squared. Do we know the velocity? Well, no, but we can calculate it because we know, according to the conservation of energy, that the total energy is conserved, which means the total energy has to stay constant. What was the total energy over here? Well, it was 39,200 joules. So that must remain constant. So the total energy here is going to be the potential energy plus the kinetic energy. This potential energy in this case is 0. The kinetic energy is 1/2 mv squared. And this total energy has to be the same, 39200. Because the total energy, according to conservation of energy, with a conservative force like gravity, has to remain constant. So now we've got a little equation over here where we can calculate now the velocity. So let's do that. 39200 is our total energy. That stays the same. That stays constant throughout everything. But you see what happens now here. This total energy now is going to be all kinetic energy. See, up here, it's all potential energy. Down here, it's all kinetic energy. All right, so all the potential energy it had at the start went into kinetic energy at the bottom. All right, 1/2 mv squared, and I could have put for m the 100 kilograms. And if we do this guy here, we find that velocity is going to equal, because I calculated this out before, and velocity is 28 meters per second. You know what, I'd like for you to stop the video here and calculate the velocity and just convince yourself that that's the case. Maybe I'm wrong, but I don't think so. This 1/2 of 100 is 50, so 39200 divided by 50, and then you take the square root of that whole thing to find the velocity, which should be 28 meters per second right there. So it's going 28 meters per second right there, and we know that because of conservation of energy. So all the energy that it had up here was all in potential energy. As it was on its trip down, it was changing. See, the potential energy was dropping. So somewhere midway here, it had both potential energy and kinetic energy, the sum total of which had to stay constant with what you started at the very beginning. All right? So what you started with, the energy you start with, has to be constant. So right over here, you're going to have potential energy plus kinetic energy. And down here on the bottom, where you basically right on the ground, you don't have any potential energy, but you have everything in kinetic energy. Now let's go to the next phase over here. Let's do red. Okay, so now it's up here. Here's our car over here. And we want to find out what's going on over here at this point. Well, at this point, the potential energy is mgh, which is the mass is 100. The acceleration due to gravity is 9.8. But in this case, it's 30 meters. So it's 10 meters down from where it started at the top. What's the kinetic energy? Well, it's moving at this point. And we know it's moving because this total, well, you know what I should have done? I should have calculated this, shouldn't I have? So this potential energy here is 29,400 joules. Notice that the potential energy here is less than the total energy here that we started with. Therefore, since energy conservation says that the total energy has to be constant, we know that if the potential energy here is 29,400, the kinetic energy has to be enough for the total energy. So let's say that the kinetic energy is going to be let's put it this way: the kinetic energy plus the 29,400 has to equal the total, which was 39200. So that's the total energy that we started with in this system up here. That stays constant, which means that the kinetic energy at this point plus the potential energy at this point has to be equal to that. So the kinetic energy at this point is simply the 39 minus the 29 over here, and that comes out to 9800 joules. See that? So the kinetic energy at this point is 9800 joules. If we wanted to find out what velocity of your roller coaster car is at that point, the kinetic energy is 1/2 mv squared. So that's 9800 equals the 1/2 the mass, which is 100, times velocity squared. And we've solved that for velocity. Velocity in this case is 14 meters per second. So why do you think the velocity here at this top is slower than down here? Well, because the kinetic energy here, right, some of that kinetic energy went into potential energy to lift it up. So the kinetic energy at this point is less than the kinetic energy that it started with, because some of this kinetic energy went into potential energy. So take another look at this, and hopefully this will get a little clearer as you see it again, and you'll get this concept down.